시작하고 okay. Okay. Here. Yeah, now we start section 2.4 and 5. Okay, section 2.4 is about some implications of Schur's theorem, applications, and others. The first one is about Cayley-Hamilton theorem. Okay, Cayley-Hamilton theorem says every square matrix satisfies its own characteristic equation. So what it says, for every matrix in N of C, suppose fa of t is a characteristic polynomial, then this, if we prove A is as a variable, then it turns to be a zero matrix. This is a Cayley-Hamilton theorem. Okay. The first exercise on this is find the first reason of the following statement. Okay. Here is the proof that you may see. Since Pa of t is a characteristic polynomial of A, so it can be written in this way. Okay. So we can put A instead of t. Then we have determinant of ai minus a here, which says determinant of a minus a says determinant of zero matrix, so which is 0. Okay, so we can say Pa of A is equal to 0. Very simple proof of Cayley-Hamilton theorem. Do you think this is a right proof? Chong. This proof, if the proof of Cayley-Hamilton theorem is this simple, then it wouldn't be that popular. This proof is wrong. What's wrong? What's wrong of this proof? Chong? Hana? Yeah. What's wrong? Ti. T here. Yeah. Okay. Is not, so we cannot do this. That's what you think? But that's not that true, because we had this. If we put A on this place, now what we have is a product of two matrices. It is well defined. Songtae, what's wrong on this proof? Assumption? Characteristic polynomial is a real, yeah. Characteristic polynomial is a real. Characteristic polynomial is not real. It can be complex, but actually it's a scalar. It's a scalar. So yeah, you made the right point. Cayley-Hamilton theorem says the right-hand side is same as left-hand side. here this is a zero matrix. This is a matrix, and this is another matrix. And the Cayley-Hamilton says these two matrices are same. There's nothing wrong with this, but here, this part is okay, because determinant of ai minus a is a scalar. This is a scalar, and this is a scalar, and this is a scalar, 0. That's true. It works. But what we are saying here is PA of A is equal to a matrix of size n by n, whose all entries are 0. So even though we have this, we cannot have this. We cannot say this matrix is same as a 1 by 1 matrix, because this is a n by n matrix now. This is a 1 by 1 scalar, and this is a 1 by 1 n by n matrix. They are not same. They are same. PA of A is an n by n matrix, not 0, not a scalar. So when we think of this is just, as you see, an minus this is this form of matrices. That's why it's very important when you write mathematical forms. You should use a proper notation. You have distinct with the scalar, with the vectors and matrices. Okay, you see the difference? Okay, here, as I told you, the Cayley-Hamilton theorem says this matrix is same as this matrix, not with a real number or scalar. Okay. Okay, then let's now see the real proof. Now see the proof of the Cayley-Hamilton theorem. This is the one of the beautiful proofs of Cayley-Hamilton theorem. We know this equality. A times adjoint of A is the same as the determinant of A times an identity matrix. Okay? Replace A by lambda in minus A. So we substitute this on the above equation, then we have this. Okay. Then this is a matrix, and this is another matrix. Okay, but as you see, each entry of this matrix is a polynomial of degree at most n minus 1 in A, because the joint of this matrix, each entry is a determinant of a submatrix of the size n minus 1 by n minus 1. So we cannot have a matrix of this form in this polynomial, not the degree not more than n minus 1. Okay? So we can write it as a summation of matrices with the coefficient lambda. Here is lambda. Here lambda is we can write this adjoint matrix as a linear combination of matrices with these scalars. Okay. Because every matrix has some lambdas here with the matrix, and so we can every entries has lambda 0 to lambda, so n minus 1 in between. So we can rewrite this adjoint matrix as a linear combination matrix with these scalars. Okay, and also the determinant of lambda in minus a can be written as this scalar, this polynomial of lambda. Actually, it's a scalar. Okay, so with this, we can put this one here and that one here. Then, left-hand side can be is same as this right-hand side. Okay. Then we can think this as a polynomial in lambda with all degrees in this way. So this is a matrix polynomial, and this is another matrix polynomial. Now we have the matrix polynomial with a variable lambda. If these two matrix polynomials are same, what that means is all the coefficient matrices are same. Every coefficient matrix are same. So what that means is this Cn and this Bn minus 1 should be same, and so on. So if we rewrite it in this way, this coefficient should be same as this one. Since this is a matrix, that one should be, the in should go with it. And the very last one is same as this. But all the terms in the middle, are kind of overlapped. Here, there are two terms. There are overlaps. So we know that this is just since these matrix polynomials are same, all the coefficients are same like this. So how we deal with this? We know if we multiply an here, a to the n minus 1 here, and a and I here, and if we add the product of these matrices on these matrices and adding it, then what do we have? We're gonna have a characteristic polynomial with the matrix of the matrix A here. Okay, but let's see. So this is going to be our right-hand side of the original one. But if we multiply a n here and a n minus 1 here, a n minus 1 here like this, then what do you see? These two are cancelled. If you multiply here a here and a here, these two are cancelled, and these two are cancelled. Okay, we should have the right side, not this side. Here, the right side. Then these are all cancelled, and we have a zero matrix here. Does it make sense? So what we did was we compared the coefficient of these matrix polynomial, and we multiplied the power of the matrix A with our intention to make the polynomial of matrix which has the same form of the characteristic polynomial. Then we saw all these are cancelled and left hand side should be equal to 0. This was the right hand side and this was the PA of A. So now we know this is equal to a zero matrix, which means this matrix A satisfies its characteristic polynomial. Now it proved the Cayley-Hamilton theorem. There's nothing complicated in this proof. There are many ways of prove Cayley-Hamilton theorem, but this is one of the beautiful proof on the Cayley-Hamilton theorem. Okay, there are many corollaries. Corollary 2.44. If A is a non-singular matrix, then A inverse can be written as a polynomial in A of degree at most n minus 1. A inverse can be written as a polynomial in A of degree at most n minus 1. Since Cayley-Hamilton theorem, we have that. If we rewrite it in this way, it can be written in this way. So C naught times identity matrix can be written in this way. Since A is non-singular, A inverse exists. So we multiply and okay, yeah, we can divide this with the C naught because C naught is not equal to 0. There's a reason, and A inverse exists. So A inverse can be written as this. You know what that means? That means, suppose we have a matrix of this form, then we know we can easily find the characteristic polynomial of it. Okay? Then we know it satisfies, the matrix satisfies that characteristic polynomial. From here, we have A square, so like this. Then we can always find A first, which is a square of these two matrices. And also it can be simplified with this in any times. So any power of these matrices can be written as a linear combination of the power of the matrix A, but its degree is at most n minus 1. Here it was a 2 by 2 matrix, but every power of the matrix can be written as a linear combination of the matrices A or I. That's it. Okay. With this knowledge, we can find the A inverse as well. Since we can easily find the characteristic polynomial, so we know it satisfies A matrix A satisfies this characteristic polynomial. So it can be written in this way. So I can be written in this way, but that means it's A inverse can be found by just addition and subtraction of the power of matrix. Also, its degree is not more than n minus 1. So this is another way of using the Cayley-Hamilton theorem. So when you find the inverse of a certain matrix, you can also use Cayley-Hamilton theorem. Isn't that nice? This is just sometimes it can be very useful to do it. Okay, next. Theorem 2.4.6. What it says is every diagonalizable, all diagonalizable matrices are dense in Mn over C. This is what this theorem says. All diagonalizable matrices are dense in the set of matrices. What that means is if A is an n by n matrix, then for arbitrarily chosen epsilon, there exists a matrix A of epsilon such that the two norms of A minus A epsilon is less than epsilon, and this matrix is diagonalizable. So whenever we have any matrix, we can find a diagonal matrix which is very close to the given matrix. Does it make sense? Oh, it depends on epsilon. So suppose we have a matrix A here, then we can add some epsilon here and there. So the basic idea is this. A is similar to a T required as Schur's theorem. This is all implications of Schur. Here, if A has distinct eigenvalues, what that means is the diagonal entries of this T are all distinct. Then A is diagonalizable. But A may have the same eigenvalues and also may have less geometric multiplicities than algebraic multiplicity for some eigenvalues. So, if we add, if in that case, if A is not diagonalizable, we may just add T11, T22 here, Tn here. We may just add some epsilon here and here for some to make it distinct. Then this can be a matrix of T with some variation by adding some epsilons on certain places. Then this is what? This is diagonalizable, isn't it? But the distance between these two may not be that big, isn't it? That's the idea. So proof goes in this way. By Schur's theorem, there exists a unitary matrix U such that U star AU is T. Let E be a diagonal matrix with EIs on the main diagonals. Those are EIs are just numbers, scalars, chosen. Absolute value of EI is less than the square root of epsilon of n. Then, so all of the diagonal entries of this new matrix are distinct. Okay? Then, this matrix T plus E are diagonalizable because T plus E is an upper triangular matrix and all the diagonal entries are distinct. So it is a diagonal matrix. Since T plus E is a diagonal matrix and A is equal to U, T U star. U times T plus E times U star can be written in this way and this way. This is similar to T plus E. Okay? So we can tell this matrix is diagonalizable. Let's A of epsilon is this. Okay? Then A minus A epsilon is this matrix. And the two norms, the square of two norms, can be counted in this way, entry-wise. But everything's the same except the diagonal entries. But we added these numbers, which is less than this. So summation of that cannot be more than epsilon over n. We have n of them. So even with all together, that does not exceed the epsilon. So we have developed A of epsilon with A plus U, E, U star. Like this. That's okay. So we in matrix theory, we call this is a theorem for the almost diagonal. Even if you just give me any matrix A, I can find a diagonalizable matrix, and whose distinct is very small. So in the real problems of engineers, they don't have to worry about the whole matrices. They only worry about the diagonal matrices, which makes everything very simple. All the theory that those assumptions are possible and those simple calculations are possible are based on the sure theory. These are all comes from sure theory. In analysis, we say diagonal matrices are dense. The set of matrices. Okay? And some notes here. Let D alpha is this. Then D alpha inverse can be written in this way. If we multiply D 1 over alpha and D alpha on both sides and find the ij's entry of this matrix, ij's entry of this matrix, then by the 3m notation, this ij's entry is a product of this I slope and A matrix and J's column of D alpha. So it can be written in this way. What that means, we just multiply alpha times alpha 2dj minus i's power times ij's entry of a matrix A. Okay? What this means is by a similarity transformation, we can always control the size of each entry of a matrix. This is all with the similarity. If we combine this knowledge with the Joule theorem, we can start to simplify the matrix T as much as we can. This is a start to find the Jordan canonical form and all others. Same thing here. If we find this type of similar matrix and ij's entry of it, then all the only difference is alpha times alpha to the I minus 6 power times A ij entry. what this means is this is entry of this A matrix. If we give this similarity, we can control the size of this matrix, this entry. Okay? With this, we can find a Jordan canonical form by using Schur's theorem. You understand? A is here. We have a T matrix here. With T matrix here, we can control. We can have a control of all others here. When you multiply this one, all the similarities are going on. We can make many are here are very small. Also, we have learned what if the eigenvalues are distinct, then we know they are the corresponding eigenvectors are orthogonal, and we can find also normal vectors. And in that case, we can find the direct sum of it, isn't it? If here is a lambda 1i and lambda 2, lambda c are different, then we know those are all like this. And we don't know this part. So all we have to worry about is only this block. On this block, we use this similarity to make all others as zeros as much as we can. So all these are treated in chapter 3 or 4. Yeah. Okay. Next. These are all the implications of Schur's theorem. Another important remark. Let's say A and B are commute. Then alpha I plus beta j should be an eigenvalue of A plus B. Let's see an example. Let A and B are diagonal matrices. If they are diagonal matrix, they are definitely commute. They are commute. But think, what's the eigenvalue of A? It's 1 and 2. The eigenvalue of B is 3 and 4 because they are all diagonal matrices. The addition of those two eigenvalues, 1 and 4, are 5. But it is not an eigenvalue of A plus B. Okay. So even if A, B are commute, the eigenvalue is of both matrices, two matrices, still is not an eigenvalue of the addition of those two matrices. But we can say the set of eigenvalues of A plus B is a subset of the set of eigenvalues plus set of eigenvalues of B. Okay? This is a lot larger groups because you know what this means? No? This set is here 1 plus 3 and 1 plus 4 here, and 2 plus 3 and 2 plus 4 here. This is 2 by 2 matrices, but eigenvalues of this can be 4. And this set of entries are 4. So here we have only 2 entries, here 4 entries. Okay, anyway, yeah, so this is one fact that you should know. But if the matrices are not commute, then those matrices are simultaneously, they are not simultaneously diagonalizable. So we cannot even say this inequality, this inclusion. If they are not commute, that this may not be true. This is only true for the matrices that are commute. Here's an example. A and B, they are two 1 by 1 matrices, but they are not commute. The eigenvalues of A plus B is this, because that's diagonal matrix. But the eigenvalues of each matrix are only zeros. So summation of those two sets is still only 0. This does not include any one of these. So this is true if AB is equal to BA only. The property of the commutativity is a very strong property, but when you think the properties of eigenvalues, we see a totally different behaviors. So it gives us a motivation to study more. So here is the theorem. 2.49 that A and B are n by n matrices that are commute, and say lambda i's are eigenvalues of A and mu i's are eigenvalues of B. Then there exists a permutation alpha such that the set of eigenvalues of A plus B can be written as a summation of those two eigenvalues with the different index depend on their permutations. This is possible if A and B are commute. What this means is this. This is a remark that we saw a minute ago. This is possible because they are commute. Because they are commute, A, B are commute. So they are simultaneously diagonalizable to upper triangular matrices. So there exists a unitary matrix U such that U star AU can be written as this way, and U star BAU can be written in this way. Here the lambda i's are the eigenvalues of it, and here mu sigma of i's are the eigenvalues. We can always give a number as we wish. So this, let's say these are the, we have the eigenvalues are here in order. We know these has a different orders, so we can just give a new index because that's the permutation. Important thing is, think U star A plus B, U. Think about it. Then this is a summation of these two matrices, which means the sum of these two matrices, which is this. Isn't it? What's the eigenvalues of this matrix? This. Only thing is just here we have some permutations, just change of orders. That's all. So if it's commute, then we can clearly say something about the eigenvalues of the addition of two matrices with the given information on the eigenvalues of each matrix. Okay? Here in section 2.4, you can think 2, 3, 2, 3, horror 4, Jung 5, Jin and Kim, Hana 12. And these are the very very interesting problems that you should know. Okay, same thing. Okay. Okay, next section is about the normal matrices. Any questions before we go through? So, yeah, we have studied the Schur's theorem and the various versions of Schur's theorem and the applications of Schur's theorem. Now, we're going to start normal matrices, which is a very interesting class of matrices. Normal matrix. normal matrix is so important because this gives us if and only if condition for the diagonal line. This if and only. It's very important. Many mathematicians worked hard to find the necessary and sufficient condition for the diagonalizability of a given matrix. This was the answer. Okay, normal matrix. Okay, here, definition. A matrix A is called normal if A star is equal to A star A. Very simple condition, isn't it? Very easy to find. If they are same, it's done. It's normal. Here is the examples of a normal matrix. All unitary matrices are normal. All Hermitian matrices are normal. And all skew Hermitian matrices are normal. Okay, so this normal matrix is a very powerful. Has a wide range of views. But there are some matrices which is normal but not unitary. Which is Hermitian, which is normal but not Hermitian. There are example matrices that are normal but not skew Hermitian. You can easily find the one. For example, this matrix is definitely is a Hermitian, but definitely is a normal, but it's not unitary. Because they are orthogonal, the columns, but the lengths of each column are not one. So it's not unitary. So these are the matrices. These are the matrices which is not unitary but normal. And you can also find the other examples. The other difficulties. Okay. Here. Spectral theorem for normal matrices. This is called a spectral theorem because it deals with the eigenvalues, actually. Spectral theorem. Okay, if A is an n by n matrix and lambda i's are eigenvalues of A, since we are in a field which is algebraically closed, so we have n eigenvalues, counting multiplicity. Okay. The following is equivalent. A is normal, A is unitary diagonalizable, is if and only if. If and only if the two norm, the square of it is the summation of square of each eigenvalues. If and only if there exists an ON set of eigenvectors of A, they are all equivalent. So if you just show A star is same as A star A, then you can tell everything like this. You can just say it is the unitary diagonalization, and also it has ON set of eigenvectors without hesitating a minute. Okay? Oh, proof. Here is my tactic to prove this equivalence statement. I will show this A and B are equivalent first. Then show and this B and C statements are equivalent. Then show this B and D are equivalent. Then I can show everything is equivalent. Okay? first. A implies B. Then show B implies A. Okay, here. A is normal. We start with normal. We know A star A is equal to A star. Okay. We want to show it is unitarily diagonalizable. By Schur's theorem, there exists a unitary matrix that U star AU is an upper triangular matrix T. Okay? Then U star A star U is equal to T star. It's by Schur. Okay. But this T star should be same as T star T because A is normal. They gotta be same. Now all we have to show is this upper triangular matrix T is a diagonal matrix. Then we showed the matrix A is diagonalizable, unitarily diagonalizable. So all we have to show is this T matrix is diagonal. Okay. What that means is, what that means is, suppose T is a triangular matrix, and it is normal, then it's always a diagonal matrix. This is what we are trying to show. Okay. We prove it by mass induction on the size of the matrix. And N is 1, definitely it is trivial. It's a 1 by matrix. It is a diagonal. Assume true. 1 minus 1. Now we show it is true for N. Okay, now we think 1 entry of the right hand side. Okay, and left hand side. 1 entry of this right hand side is this. But 1 entry of this left hand side is this. Because T is an upper triangular matrix. Here we say T11, T22, Tnn here, and zeros here, and Tij's are here. Okay? Here, when you multiply this with A star here, then you have to multiply non-zero entries there. But if you multiply the other way, then you just multiply this and that. So these are all zeros. So you just only have this one. But as you see, these two are same. So this 1 entry and this 1 entry should be same. What that means is this one should be same as this one. But this is same as this. What that means is this part gotta be all zeros. As you see here, Ti1j here and T1j bar. So this is the square of absolute value of each of diagonal entries. So this is all of diagonal entries. Square of it is 0. What that means is all T1j, the value of it is 0 for all j's from 2 to n. What that means is this. Okay? Then we can let T be a T11 direct sum with T1, which is a n-1 by n-1 matrix. But T star is equal to T star T. So this Ti is also satisfying this. That's their normal matrix over smaller size of n-1. So we can use mass induction because this is the normal matrix with a smaller size. So by the induction hypothesis, T1 is a diagonal. this is a 1 by 1 matrix with a direct sum with the smaller size of diagonal matrix. So T gotta be a diagonal matrix, isn't it? Very simple and nice, clear proof showing this T is a diagonal matrix. This is a very standard technique of showing. When you deal with the matrices, we think the entries. By Schur's theorem, you can always think triangular matrix. Then you multiply T with T star in one side, then you have the very simple form in one side, and some others, some with extra terms like this on the other side. You can always compare. And mass induction is the one that you can reduce the size of the problem. Okay. Next, the other direction from B to A. Suppose A is a unitarily diagonalized. We want to show A is normal. There exists unitary matrix U such that U star AU is equal to D diagonal matrix. Then A can be written U D U star. Then you can calculate A star and also A star A. You can see they are all same. If it is unitary diagonalizable, then A star is equal to A star A. Because A can be written as a D U D U star. Here U D U star and star of it. This just goes all the way in this way. If you have a diagonal matrix, then for the diagonal matrix, D star the same as D star D, because you just multiply scalars on side. There's no difference which one has the conjugate on one the other. So it doesn't make any difference. So this is very easy. This is because you have spent some energy for showing the other way from A to B. So the opposite direction, proof of it, is much easier than others. Okay. Next. Show B implies C and C implies B. Okay. Then here we want to show when U is a unitary diagonalizable, then we satisfy this. Since it's a unitary diagonalizable, there exists a unitary matrix U and diagonal matrix D here. Then the two norm of that matrix U is same as two norm of that diagonal matrix. The diagonal matrix, so the diagonal entries are the eigenvalues of A, so they should be same. Very easy. And next, suppose we have this. We want to show this matrix A is unitarily diagonalizable. We can use the Schur's theorem here. If U star AU is equal to T, which is an upper triangular matrix by Schur's theorem, then we know those two norms of are same. That's because U is a unitary matrix here and here. U is a unitary matrix, so it works. Okay, then the square of the two norm of A is same as this. This is a given condition of C. Think about the two norm of T, the square of A. Then this is the summation of those diagonal entries and extras. But we know these two are same. So these two should be same, but they are already same, so this gotta be equal to 0. But that means is all the off-diagonal entries are 0. Okay? So this T should be a diagonal matrix. Okay. Yeah. For Dn, the equivalence statement between B and B, this is about this. A is diagonalizable, then there exist n linearly independent eigenvectors of A. Here is normal, it's unitary diagonalizable if and only if there exist also ON and ON vectors of vectors of A's. This is what we have already shown. So we have proved very important and very useful equivalent statement on normal matrices. Now you have if and only if statement for the diagonalizable, particularly unitarily diagonalizable. It all comes from Schur's theorem. This is a topic of a little over the elementary introductory linearity. Before you learned how you diagonalize a matrix when it is diagonalizable, but you haven't learned the if and only if statement of that. But here now you have the if and only if statement on the diagonalizable with many different versions of it. So now you can always think and deal with the diagonal matrices if it is diagonalizable. It is easy because you can always check when a given matrix is diagonalizable by the above equivalent statements. Next, 2.4.5.5 theorem. If R is a commuting family of a normal matrix, then R is simultaneously unitarily diagonalizable. Here, the only difference is normal matrices. It's the same thing on the commuting families, but when you have a normal matrix here, when you have a commuting family, you have a simultaneously diagonalizable. Here, if you have a set of commuting matrices that are normal, then you have a unitarily diagonalizable with the previous property of simultaneous diagonalizable. Next, 2.5.6. A is Hermitian. Then all eigenvalues of A are real. And A is unitarily diagonalizable. And also, it's not like that. They are, if is a Hermitian, then all eigenvalues are real, and A is unitarily diagonalizable. If A is a real symmetric matrix, then A is real orthogonally diagonalizable. That means you can diagonalize a matrix with a real orthogonal matrix instead of a unitary matrix. Okay. Here the textbook gives us these two parts. First, if A is a Hermitian matrix, which means A star is equal to A, then by sure, then since it's a Hermitian, so it is a normal matrix. So it is unitarily diagonalizable like this, isn't it? It is diagonalizable. So we can think the eigenvalues of A star. That's just a conjugate of this. But since it's a Hermitian, they should be same. That means these eigenvalues are same as well. That means each eigenvalues is same as its own conjugate. What that means is they are all real. They are all real. Okay. Next, it is unitary diagonalizable. A is Hermitian and A is normal, so A is unitarily diagonalizable, but it is it's done. And what else? And part C. If A is a real symmetric, it is a Hermitian. So every calculation that diagonalizes that real symmetric matrix are done with the real entries. And it's all eigenvalues are real. So it's all eigenvectors should be real too. AX is equal lambda x here. This is a real matrix. All the eigenvalues are real. And it's all the diagonalization here, and it's such as like this here. U here, and D here, like this. These are all real, and those are the older reals. So this matrix U formed with this unitary diagonal matrix are formed with reals, and these are the reals. Here U star AU is equal to D here. These are all reals, but that means this is real matrix. Real Hermitian matrix is real symmetric matrix. So that's why. What that means is if A is a real matrix, then we can think U transpose A U is equal to eigenvalues here. Because this is our reals and this is our reals. The eigenvectors which forms the column vectors of U are all reals. So we say A is real, also when I diagonalize. It's just a special case. It's because it's all done. Real number computation. Theorem 2.5.8. Here. A is a normal if and only if there exists a real orthogonal matrix Q such that this. Here, these AIs are either 1x1 real matrix or 2x2 real matrix of form this. This is what I told you before. Okay? Next, another corollary. These are all follows from what we have learned. If A is a real matrix and A is equal to A transpose, then there exists a real orthogonal matrix Q that Q transpose A Q is like this. And these all lambda i's are real. This is what we taught. Section 3. If it's a skew Hermitian, skew symmetric, it's a real matrix, so it's skew symmetric, then there exists a real orthogonal matrix Q such that Q transpose A Q is written this way. Okay? Here all reals because it's a real symmetric matrix, so all eigenvalues are real. But here is a skew symmetric matrices. So all the eigenvalues are all zeros or all complex. So all zeros are here and all complexes. So from the previous corollary, these complex eigenvalues can be written as a similar matrix of 2x2 with the real entries. Okay? This is pure eigenvalues. Those beta j's are pure imaginary. So actually these are pure imaginary values of real skew symmetric matrices. You understand that? Okay? This is all the consequence of Schur's theorem. Okay. If A transpose is identity, then there exists a real orthogonal matrix Q such that Q transpose A Q can be written in this way, the orthogonal matrix. In that case, all the eigenvalues are plus minus 1 or some complex numbers, but whose length is 1. Here and here or here. Okay? The orthogonal matrices. What important thing is the eigenvalues. The lengths of eigenvalues are 1s for all I. Isn't it? Is that right? If here and here, then that's the real eigenvalues. So here you have real eigenvalues. Here you have complex eigenvalues. The complex eigenvalues are on this unit circle. This is because you can, all of eigenvalues can be written cosine theta j plus I sine theta j, something like this. Isn't it? plus minus. So we can find the similar matrix. Whose entries are real part in the eigenvalue. So complex. Okay. So these are all the consequences. So in section 2.5 here, so there are some problems. I think there are too many problems to one day. I may extend this one for 2 weeks. Here, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 19, 23, 24, 27, 28. These are the facts that you should know. If you know those problems, then you will have any difficulty to use the knowledge that you have learned. And those particular problems are carefully chosen. It's not, it doesn't take too much time. Not very technical, very theoretical, and you can easily follow. Okay, the next thing is QR factorizations. QR factorization. Is there anyone who recall the QR factorization section in the elementary textbook that did you to look at QR factorization? Linear 7 Hana look at factorization. Not you have, because it's an analytic theory. Some so important factorization. This factorization is a find a kind of relation of matrix with unitary upper triangle matrix. And factorization in LUT are all matrix. Those are important, but there's form of factorization, decomposition, decomposition, those chapter 7 matrix. So those basic factor factorization have in this address contemporary day. You go here, everything. There are more in numeric I have given. Okay, and more address. You 34 to go this section is here. Suppose we have a matrix A, then that can be written as QR with a unitary matrix Q and upper triangular matrix R. If we can do so, what we can do is this. Okay. We can do here. The reason for that, reason for learning QR factorization is when you solve AX is equal to B, the linear system of equation, usually the A may not have an inverse matrix. Even A usually not the rectangular, not the square matrix, it's a rectangular matrix. So we cannot use the inverse of it to solve. And also the size of that matrix is quite large. But if we multiply A transpose on both sides, we can have this system of linear equation. In case this matrix A transpose A has an inverse, then we can find the solution easily, X, with this. Even though A is not the square matrix. This is called the least square solution for a given linear system of equation. But here, this process also takes some work to find an inverse of matrix. But if we use the QR factorization here, this problem turned out in this way. If A can be written as a QR, where Q is a unitary matrix, then this linear system of equation can be written in this way. Because A is equal to QR, QR here, QR transpose here. And you just go through it as this. Okay, this A transpose X can be written, is equal to A transpose can be written in this way. Here, R is an upper triangular matrix. Okay, here. So here is the left hand side is this. So left hand side. Okay, TB. So left and suppose and here also this Q transpose Q are gone because Q is a unitary matrix. The identity is R and this R Q transpose one single when A we can this R can singular and this can be but we have application have system like solving the but it's a double matrix which triangle the solution to do solving this triangular matrix. So we just the back version together we can find the in this way. Okay. So the matrix so very problem. This but I gave developed the I used that the tool some problem. Some problem by
6. So here, but the difference here is here I have trivial case.
of n by n matrix with full length. The general with this our two content is a general on Q for on first. Show you Q alpha. You on it.